This is a standard ruler. It features 30.5 centimeters on one side and 12 inches on the other. It's a pretty good tool, though for most jobs around the house, nothing beats a good tape measure. I have two because there are two main systems of measurement, metric and stupid. But do you need to know the distance of something a tape measure can't possibly reach? That's why we have kilometers and miles. Do you need to go smaller? We have millimeters and a bunch of annoying fractions. But if you need to know extreme distances, say the space between galaxies or the size of a proton, these units no longer cut it. So today I'll be looking at extreme units of measurement concerning distance and, since it's related, speed. Speed for the most part is pretty basic. There aren't many units that deviate from the standard distance per time ratio. This is all the average person needs because as long as you understand the basic units of measurement used here, you can easily get a reference for speed. I can tell you that some seahorses travel at 5 feet per hour, and bullets move up to 1500 meters per second, and you can easily get a sense of how fast they're moving. A unit of high-speed measurement often heard of, typically in reference to air travel, is Mach speed. The simple formula to figuring out Mach speed is the speed you're traveling divided by the speed of sound, 1,234.8 kilometers an hour. Now this number represents the speed of sound through air that is 15 degrees Celsius at sea level because it differs depending on factors such as altitude and air temperature. Airlines typically travel between Mach 0.652 and Mach 0.717 with a speed limit of Mach 0.8. Flying too close to Mach 1 would cause incredible drag, severely reducing the fuel efficiency of the engines. There's a really cool video from Wendover Productions discussing why planes don't fly faster, even though getting past Mach 1 once again causes drag to drop. I have the link in the description. Flying at Mach 2 would mean flying double the speed of sound, Mach 3 triple, and so on. Military jets typically travel between Mach 2.5 and Mach 3, with the record for fastest manned jet being the Lockheed SR-71 Blackbird. This jet was used between December 22, 1964 and October 9, 1999 for reconnaissance missions and experimental research, with speed being its main weapon. In nearly 35 years of operation, not a single one of the 32 Blackbirds was so much as damaged by an enemy fighter or surface-to-air missile, thanks to its record speed of Mach 3.3 or 3,529.56 kilometers an hour. This was achieved on July 28, 1976 when it was crewed by Captain Eldon Joares and Major George Morgan. The plane was so fast that on September 13, 1974, the Blackbird, crewed by Captain Harold Adams and Major William McCorrick, flew from London to Los Angeles in 3 hours, 47 minutes, and 39 seconds, covering a distance of 8,765.89 kilometers at an average speed of 2,310.36 kilometers an hour. Lockheed Martin is currently working on its predecessor, the SR-72, an unmanned plane that will be capable of reaching Mach 6, over 7,240 kilometers an hour. But even that is nothing compared to a space shuttle, which could reach speeds of Mach 25, 28,160 kilometers an hour upon re-entry. Then there is the speed record, Mach 874,030.49. Of course, I'm talking about the speed of light, sometimes referred to as the speed limit of the universe. Light travels an astonishing 299,792,458 meters per second, fast enough to traverse the equator nearly 7.5 times in that span. At that speed, it takes light 8 minutes and 19 seconds to reach the Earth from the Sun at its average distance of 149,597,870.7 kilometers. That distance has a special name called an astronomical unit, or AU, and it's a good measurement for discussing distances within our solar system because it gives you an easy comparison to the distance between the Earth and the Sun. You could say Mars averages 227,900,000 kilometers from the Sun, and Pluto is 5,913,000,000 kilometers away, but it's much easier to comprehend by saying they are 1.52 and 39.53 AUs away. The Voyager 1 spacecraft is currently just over 138 AUs from Earth, over 20.64 billion kilometers, a round trip that would take light 38 hours, 15 minutes, and 27 seconds to travel. And if you're interested in an up-to-the-second update on Voyagers 1 and 2, be sure to check out NASA's Jet Propulsion Laboratory website. I have a link in the description. The Oort cloud, the spherical shell of icy objects that encompasses our solar system, is between 5,000 and 100,000 AUs away, 748 billion to 14.9 trillion kilometers. The Oort cloud is believed to be the origin of long-period comets, those that take more than 200 years to orbit the Sun. To really put this in perspective, check out the Scale of the Universe created by Carrie and Michael Huang. It's one of my favorite web pages, and it's so much fun to scroll through and try to understand the relative sizes of different objects. Again, the link is in the description. But if you want to discuss farther distances, such as the space between the stars in our galaxy or between the galaxies themselves, you need to use light years. Often confused with a unit of time, a light year is the distance light travels in 1 year. This comes out to 9.46 trillion kilometers, which would make the Oort cloud between 0.079 and 1.581 light years away. Unlike light speed, however, you can continue to use a higher measurement. Astronomers also use parsecs, which is defined as the radius of a circle for which 1 arc second has the length of 1 AU. You know that a circle has 360 degrees, while each degree is made up of 60 arc minutes. Each one of those is made up of 60 arc seconds, meaning a full circle contains 1,296,000 arc seconds. So a parsec comes out to 30.86 trillion kilometers, or 3.261 light years. This distance is important because scientists use this calculation to figure out how far away distant objects are using a type of math called parallax. To put this in perspective, the closest star to us is Proxima Centauri, which is about 4.243 light years or 1.3 parsecs away. So even if we could reach the speed of light, an impossibility for anything with mass, it would still take nearly 4 years and 3 months to reach our closest neighbor. At Mach 1 it would take 3,708,511 years, and traveling at conventional highway speeds of 120 kilometers an hour, it would take 38,160,582 years. Plus, 4.243 light years is much easier to say and comprehend than 268,331.81 AUs or 40.1 trillion kilometers. On the opposite side of the scale, there aren't really any imperial units smaller than an inch, other than repeatedly cutting sections of it in half, except for the thou, 1/1000th of an inch. And in metric, you could just add whatever prefix you need to the meter depending on how much you move the decimal over. Protons and electrons are around 1 femtometer, 10 to the negative 15 meters, and neutrinos are about 1 yoctometer, 10 to the negative 24 meters. And at the extreme end, after a whole lot of nothing, you have the Planck length, approximately 1.61605 times 10 to the negative 35 meters, or 6.3624 times 10 to the negative 34 inches. This is the smallest distance that has any meaning and is how big those strings are in that one theory. I can't remember the name of it. It's also smaller than the observable universe is large. What I mean is, if you take the base unit meter and multiply and divide by the same number, let's say 10, giving you a decameter and a decimeter respectively, one would be as big, 10 meters, as the other is small, 1/10 of a meter. A kilometer at 1,000 meters is as big as a millimeter, 1,000th of a meter is small. A gigameter of a billion meters would be equal to a nanometer, 1/1000th of a meter, and so on. So the approximate diameter of the observable universe, estimated to be 93 billion light years, equals 8.79 times 10 to the 26th, or 879 septillion meters, a number 9 digits shorter than the Planck length. If you want a scale you can see for yourself, the width of a human hair is about halfway between these two distances. But here's a question. How many Planck lengths wide is the observable universe? There would be 6.18 times 10 to the 19th Planck lengths in a femtometer alone. 61 quintillion. That means in a meter there would be 6.18 times 10 to the 34 Planck lengths. 61 decillion. And that would make a kilometer 6.18 times 10 to the 37th Planck lengths. 61 undecillion. A foot would have 1.88 times 10 to the 34 Planck lengths, 18 decillion. And for a mile, 9.95 times 10 to the 37th Planck lengths, 99 undecillion. In an astronomical unit, there are 9.25 times 10 to the 45th Planck lengths, 9.2 quattordecillion. In a light year, 5.85 times 10 to the 50th Planck lengths, 585 quindecillion. In a parsec, 1.9 times 10 to the 51st Planck lengths, 1.9 sextillion. And in the observable universe, everything we can possibly see, the shortest distance can stretch across the diameter of this massive bubble, 5.44 times 10 to the 61st times. 54 Novem Decillion. The two ultimate extremes, from the smallest thing to everything. These measurements may not mean a whole lot when planning your next road trip, but in trying to understand the universe in which we live, from the smallest building blocks to the immense vastness of space, this is what is required. My name is Tim, and thanks for watching.